To continue to discuss our transformations, we will now look at horizontal stretches and compressions. So this would be stretching or squeezing our graph horizontally. Now, since it's a horizontal stretch or compression, then what that means is that we will be affecting the input. So notice we have our parent function again, f of x equals the square root of x. G of x is 2 times x and then take the square root. So notice 2 is affecting the input of the square root before the square root is taken. Likewise, the 1/2 is applied to x and then the square root function. So we will see a horizontal movement. So what is the parent function? The parent function, we've already said, is f of x equals the square root of x. So we have our same values, same key points as before for our square root function. And now let's look at what we have to do to obtain the graph for g of x. The first thing that we are doing is doubling x. So if I want to take the square root of the same values, I can take the square root of 0, take the square root of 2 times 0, and that will give us the same output. Now, if I want to take the square root of 1, I'm going to have to multiply 2 times 1/2 to get that input to be the same. So we would have 1/2 here, and that would be the square root of 2 times 1/2. Well, 2 times 1/2 is 1, so the square root of 1 is 1. And then, to take the square root of 4, I need to take 2 times 2. So let's use x is 2. So this would mean that I'm going to take the square root of 2 times 2, which would be the square root of 4, which is 2. So let's go plot those points. 0, 0, 1/2, 1, and then 2, 2. So there is G. Now what I want you to notice is this point moved there. It is now half as far from the y-axis as it once was. Likewise, if we look at 1, 1, it has now been moved to 1/2, 1. These have been compressed horizontally. They've been squished horizontally toward the y-axis by a factor of 1/2. Now, let's look at h of x. So, the first thing that we're doing to our input is taking half of it. So what we have to do is we have to start off with double of what we used to, because the first thing that we're going to do is take half. So let's have 0, and then the square root of 1/2 times 0 is still the square root of 0. But now if we want to take the square root of 1, we have to double our input. So instead of 1, we'll now be looking at 2. The square root of 1/2 times 2 is the square root of 1, which is 1. Now if we want to take the square root of 4, we're going to have to start off with double. So the square root of 1/2 times 8 is the square root of 4, which is 2. So what does this look like? 0, 0, 2, 1, and then 8, 2. So notice, if we compare to the blue curve, our parent function, we are now twice as far from the y-axis as what we once were. So our distance at, say, this point was 4 away. Now we're 8 away. So h is a stretch of the parent function by a factor of 2. We've doubled horizontally the distance. If f means take the square root of the input, then what is the input for the square root for g? Well, it's 2x. We're taking the square root of 2x. So we can say take f and apply it to 2x, and that means take the square root. And then likewise, h of x is going to be f of 1/2 x. And so what we found is that if we double the input, we have a horizontal compression by a factor of 1/2. Here, we're taking half of the input, so we have to double the input before we start. And so this yields a horizontal stretching by a factor of 2. So notice, if we affect the input by a multiple, then that will yield a horizontal or a horizontal compression or a horizontal stretch. So if a is bigger than 1, it's going to be a compression. If a is small, you have a stretch. And that will seem counterintuitive, but it's because it's affecting the input.